Hello, welcome back to PDEs. So far we have looked at all the steps to solving a PDE individually. Now we're going to solve a PDE, an actual PDE problem with all the steps included. So first we're going to look at the heat equation with heat induction. And the first case we're going to look at is a rod with 0 degree ends. I have 4 examples of a rod with 0 degree ends. This video will be example 1. So, for example 1, it says, consider the conduction of heat in a rod 40 centimeters in length, whose ends are maintained at 0 degrees Celsius for all t greater than 0. In each of problems, so in problem 9, find an expression for the temperature, U, x of t, if the initial temperature distribution in the rod is the given function. They gave us U x0 equals 50, when x is between 0 and 40. So that's how long the rod is, 40. Obviously, we're not given units, so length is just an arbitrary value, so 40. And we're supposing that our heat, our constant of diffusivity, alpha squared, is equal to 1. So that makes our life a lot easier, right? Let's write down our knowns here. So we know ux naught is 50. So right ahead, we know that that's an initial condition, right? We know that is going to be our f of x. We know x is between 0 and 40. We know that at each end of the rod, there are 0 degrees. So when x is 0, so let's write it like this. So let's do this. I could have just kept that there. Okay, I could just move it down. So this is our boundary condition. Initial condition. And our boundary conditions would be u of 0 of t is equal to 0, and u of 40, right, t is equal to 0. So at the beginning of the rod and the end of the rod, temperatures are 0. And we know that x goes from 0 to 40. Beautiful. Okay. Step 1. Also, what is the heat equation before we move on? We need to know what that is, right? In order to find the expression for the temperature, we got to solve the heat equation. So heat equation is what? Alpha squared uxx is equal to u of t. This is using simplified notation. Remember, these are just notation for partial derivatives, the sub x sub t's. So step 1 separates variables. So remember, we're using the heat equation. Instantly, we can tell that this is just 1, right? So that goes away. So we just have to do it for this one here. And remember, we define u of x of t as x of x, t of t. We go ahead and separate, so we're going to we want to find uxx. So uxx would be equal to x double prime times t, and u of t is equal to x of x t prime of t. So I'm gonna plug these back in now. I'm going to use the simplified versions. So you really should write out of whatever, but just for simplification purposes, I'm just gonna write x double prime t is equal to x t prime, right? So now we want to separate the variables, so we can start by dividing by t and x. So it would look like this. And then this would become x double prime over x is equal to t prime over t. And bam, the variables are separated. Now let's introduce our separation constant. I'm going to go ahead and put that right in the middle here. Call it lambda. Of course, it can be whatever lambda you define. Depends on the book, the way you want to do it. I'm using positive lambda here. I'll probably always use it. And from here we can write out our two ODEs, okay? So let's write our second order linear homogeneous ODE. We have x double prime minus lambda times x equals 0. And now we have our first order ODE minus lambda t equals 0, right? So here's our two ODEs. We separate the variables, we got our equations, beautiful. So now let's go to step 2. You want to solve the boundary value problem. And when we solve the boundary value problem, we want to use the second order ODE, remember? So we're going to start with this ODE here. Right, yeah, equals 0. And then remember, our boundary conditions, what were they? We have u of 0 of t is 0, and we have u of 40t is equal to 0. This video might be a little lengthy, by the way. That's why I'm kind of going fast through these steps. Now we have to rewrite. These boundary conditions, right? So we can just rewrite that really simply. So u of 0 of t is equal to x of 0, t of t is equal to 0. That tells us that x of 0 equals 0 and t of t is equal to 0. But we don't need that, so we just want this one. So that's one of them. And then we also know that u of 40 t equals 0. Right off the bat, you can tell it's just x of 40 equals 0, but just to show it out this one time, we know that that equals 0. Okay, so we have our two boundary conditions. We have our first order ODE. Let's do our case 1. So let's start with when lambda is greater than 0. Remember, when lambda is greater than 0, I define it as being positive mu squared, so it's always positive. We plug that into our ODE. That becomes minus or mu squared x equals 0. So then we solve the characteristic equation. Should know how to do that from ODEs. And that is positive minus mu. So then this is the c1e to the mu x plus c2e to the negative mu x. All right, that's a general solution. Then, for the ODE, then we go ahead and we do our boundary condition. So x of 0 is equal to, that would be c1 plus c2 equals 0. Because e to the 0 is 1. So now c1, we can do this, equals negative c2. So then x equals negative c2e to the mu x plus c2e to the negative mu x. I just plugged in the negative c2 for c1. So now this is our new updated x value. We're going to use that for our next boundary condition. X is 40 equals 0. So if you plug in 40, this would be negative c2e to the mu x plus c2e to the negative mu x. Wait. 40, negative 40. I was copying down what I had up there. We can take out a c2. Negative e to the 40x, mu, plus e to the negative 40 mu equals 0. So we know that we have to make c2 equals 0 And this out here also has to equal 0. So what could mu be for this to be 0? Mu would have to be 1. I mean, sorry, 0, right? So mu would have to be 0. For this case here, mu would have to be 0. So we want to think what would make both of these 0? Well, C2 is always 0. And then in order for this one to be 0, mu would also have to be 0. If you plug mu back into our last previous x value, that would also result in x being equal to 0. So because mu is 0 here, that also means that x is 0. And because C2 is 0, that also means that x is going to be 0. Because you can see that this is 0, e to the mu x, plus e to the negative mu x, plus 0. So then x equals 0. And if this is the case, then x is equal to negative C2 e to the 0x plus C2 e to the negative 0x. This is equal to negative C2 plus C2, which is equal to 0. So that means that this is trivial. Well, I should say only trivial solutions. And we don't want that. So we got to go to the next case. Okay. Let's do the lambda is 0 case. So when lambda is 0, this is easier. X double prime is just equal to 0 because you plug that back in, that goes away. So now you plug that in. Oh no, I already did. So then we just solve the characteristic equation. What is that? Plus minus 0. Oh wait. Yeah. Okay, so now we come up to here. We do the little repeated roots sheet. And then you should know that from second order ODEs technique. Reduction of order technique, right? Pretty sure that's reduction of order for repeated roots. Yep. So then C1 equals 0 for this case because x is 0. If C1 is 0, then x is equal to C2x. That's what we're left with. Now we use that. Let's look at the next one. If this is 40, we're left with C2 times 40 C2, which is equal to 0. That also tells us that C2 is equal to 0. If C2 is equal to 0, then x is equal to 0. So then that is only trivial solutions. We don't want that. Next case, this has to be the one. Less than 0, right? It has to be. So if less than 0, we define it as being negative mu squared. That negative is not on the inside of the square. So now we do x double prime plus, that would be mu because it was negative, x equals 0. We move that over, solve the characteristic. That becomes, what would that be? That'd be complex, so then we have r equals plus minus 0 plus minus mu I. General solution, this is complex, so we skip through Euler's formula here. Just write out the cheat. Right? And then we do our first boundary condition. We should get C1 equals 0 because sine of 0 is 0, cosine of 0 is 1. Whoops. X is equal to C2 sine mu x because C1 is 0. Using that information, let's find x of 40 is C2 sine of 40x equals 0. And this is clearly going to be non-trivial because you're going to get some non-zero, sorry, that's a mu. We're plugging in for x. Okay, this is mu x. Sorry. This is mu x. We're plugging in 40 in for x, not mu. Sorry. I was going a little fast there. Okay, so we have C2 sine of 40 mu. We know that mu has to be a non-zero value because in order for sine of 40 mu to be 0, let's write it down. So C2 is obviously 0, and obviously that's going to lead to a trivial. Or non, yeah. But let's look at this case over here. It makes that equal to 0. So we can set the inside of that equal to any value of pi for when n equals 1, 2, 3, and so on. Right? Because sine of pi is 0, sine of 2 pi is 0, sine of 3 pi is 0. Even if it's multiplied by 40, same thing. So then mu is equal to 40 over n pi. Wait, I just butchered that. N pi over 40, sorry. You can see that mu is never 0, so that is non-trivial. Well, let me write that in green. Let's do green. We like that. Okay. So now from that, we have one eigenvalue, one eigenfunction, because we have one x value. So we're going to look at this here. So x, let's do the eigenvalue first. Eigenvalue, that's lambda, is equal to negative mu squared, plug in for mu, negative n squared pi. So let's just write it like this. Sorry. That's a little bit easier, I think. No, let's just write it out because we don't have to deal with the 40 squared then. Let's just square that. That's for every n equals 1, 2, 3, so on. Okay. There's our eigenvalue. Oh, come on. Make a square. Thank you. Eigenfunction. So we have x equals c2, which is just going to be rewritten as x of n equals c to the n, because it's just arbitrary constant for any n, times sine of n pi over 40x for every n equals 1, 2, 3, and so on. So I say we're halfway through the problem now that we have determined our eigenvalue and eigenfunction. So now let's look at step 3. These are quick steps. Step 3 and 4 are quick. We solve the other ODE where we have t prime minus lambda t equals 0. This is the first order ODE. I should say first order ODE. So we want to solve it for t, of course. So t prime equals lambda t. We're going to, you can solve this right now we're going to separate the variables of a first order ODE, right? So then you just, well, actually we can just write it like this. Right? And then you have this, Anyway, integrate that. Yeah, so you can write t prime like that, and then you can move. Oh yeah. It's been a while since I did this. Sorry. You can divide that capital T over, and then you can move that little dt over to here. Right. And then you integrate both sides. So then we have natural log of t is equal to lambda little t plus, oh no, c's cancel. And then you have t is equal to, let's write it, let's just do it like this now. T sub n is equal to c sub n e to the lambda n t. So what was lambda? N squared pi squared over 1600. So then t sub n is equal to e to the negative n squared pi squared over 1600 times t. Now, you might notice that this is the first order way of solving it, but you could treat it very strangely for these kind of problems. I'm not sure if it's the correct way to do it, but I did notice that you could, see how I have this here? I was testing something. You could solve it like a second order ODE when you solve the characteristic equation. And then r equals lambda, right? So then we write out your general solution. You're going to get, right? Well, I guess that's not entirely true, right? You still have the other component of it. Well, no. R is just one value of lambda. It's not positive. Yeah, it's not positive minus lambda, so this would be the general solution. So you see, we get the same thing. So let's do this, or, right. But this is our t sub n right here. So I know it's kind of confusing how that works. This shouldn't work, I don't think. I don't think that always is going to work. I think I might have even did that in my step 3 overview video. Oh boy. But, you get the same answer. It's kind of funny. I hope it's right. But that's our t sub n. So now, let's go on to step 4. And that is finding the fundamental set of solutions and the general solution. So for the fundamental set of solutions, we're going to use x of n, t sub n, and u of x of t is equal to x of x, t of t, right? So then we can write out u sub n of x of t as x to the n t sub n. I'm dropping these of x of t for simplicity, and then we can write out some. This has to be some like new constant basically, because you're gonna have c sub n times c sub n. It will. Well, we don't have to because it's okay. Let me write it out. So because you're gonna have, where's x sub n? C sub n times sine of n pi over 40 times x times e c times c to the n e to the negative n squared pi squared over 1600 times t. So you can see here that we have a cn times a cn, so that's going to have to be a new constant. Now, from looking at this, you can see that we're going to have a Fourier sine series, right? So we know that we're going to have to use b sub n. So this is just a little trick that I'm going to use. So if you're wondering why I'm writing it as b sub n, that's because I know that it's going to be a Fourier sine series. So we write out the fundamental set of solutions. So I'm going to change this to be a b sub n, okay? And then this would be b sub n e to the negative n squared pi squared over 1600 times t times sine. You can see I'm switching the order here. Okay. So we can actually here, because this is a summation, this has to be written as a summation. This is actually our general solution here. Right. Move that down. General solution. So we can see here that we have a Fourier sine series. That means it's odd. So I can already foresee something here. So now remember, let's just go to step 5. Oh, this is an interesting problem. Initial condition and Fourier series. Right, we're going to use our initial conditions to solve a Fourier series. So we were given u of x of 0, I believe. I'll look in a second, is f of x. I can't remember what it is, if they gave us anything. Let's take a look. Oh yeah, it's equal to 50. Okay. So the initial condition is equal to 50, which is equal to, remember we're plugging in 0 in for time, so this is just going to be, the e to the whatever is going to vanish because it's going to be equal to 1. N pi over 40x, just like that. So then a sub naught is, let's take a look. So remember, a sub naught is, well, because I already know that's going to be 0 because we have an odd Fourier series, and the integral of an odd, remember this is dx. This is odd. Integral of an odd is always 0. So we can just forget about that one. Now a sub n. Negative L to L. A sub n is cosine, yeah. So then that's f of x cosine n pi over Lx equals 0. You see we have an odd function. You see we have an even function. Odd times an even is equals an odd. That is going to be 0. So once again, no longer need that one. B sub n. 1 over L, negative L to L. F of x times sine n pi over L x dx. I forgot my dx's here. You can see, oh sorry, that's not going to be equal to 0. You can see here that we have an odd times an odd, which equals an even. So this one is integratable. Is that a word? Integratable? So So let's go ahead and plug in our f of x. We know f of x is 50. We know our length is between 0 and 40. However, as you can see, this is only half of a range. They give us the length, but not the full period. It's not the full range. So, if you watched my last video on half-range expansions, you know that we are going to have to do a half-range expansion here. What they should have gave us was this, right? But they did not. Because we know the period is 80. So, because of that, let's take a look. When we do our half-range expansion, this is pretty obvious. Here's what we're dealing with right now. Let's say this is 50. This is where our current function looks like, right, up until 40. So obviously we're not going to go down here and go across the origin. We're just going to go across the y-axis here, right? Like this. But we know we have to do this anyways, because we know, if you remember, we go over the y-axis, that's in that's an odd expansion. That's an odd function, right? So because we know the Fourier series is odd, we have to do this expansion. We have no choice. If you go down here, you cannot do the problem, because then you have an even. Then you're saying that the general solution is an even series, which it's not. It's an odd series, so you have to go across the y-axis. As you can see by this, it has to be connected. This makes perfect sense, right? So, see, we're doing an odd expansion. Defined by the general solution. So then we're going from negative 40 to 40. So let's solve for b sub n. Our integration bounds now are just going to be from negative 40 to 40 of 50. The function stays the same, times sine of n pi over L. Our length is 40, sorry. Right, now we're able to put in the correct length, and now times x, right, dx. So let's go ahead and integrate this. I don't think it'll take too long to integrate this. Oh yeah, this should be 40. Length is 40. So that's going to be 50 over 40, right? So then we can go ahead and pull that out. And because, wait, because this is even, right? Sine is odd. Wait a minute. Oh yeah, because, is that correct? I'm gonna integrate it this way, see if I get the right answer, because I did it differently in my notes for some reason. I think you can just go from 0 to 40 multiplied by 2. Because remember, yeah, you definitely could do that, because this is altogether this is even, because this is an odd times an odd, which is even. So okay, yeah, because we define this as being odd. We just defined it as being odd. So this is odd. This is even. I'm sorry, odd and odd. So then it's even. So then you can just go like this. You can multiply it by 2. So this, you can take out the 50, multiply it by 2, divide it by 40, go from 0 to 40. You can 100% do this. Yeah, so now this next integration is pretty straightforward, pretty simple. We're left with 100 over 40. Times, what would that be? Negative 40 over n pi times cosine of n pi over 40x from 0 to 40. So then b sub n is 100 over 40 times negative 40 over n pi times cosine of n pi plus, that would be, because remember the 40's cancel, that's where that came from. Cosine of 0 is 0, so this would be minus, not plus because minus minus. So plus 40 over n pi. And then b sub n would just be 1. Oh, we can take out a 40, right? So let's do this. Bam, bam, bam. 100. Just take out an n pi too. Have negative cosine n pi plus 1 over n pi. Remember, cosine of n pi is equal to negative, well, no, negative 1 to the n, right? Plus 1 over n pi. Oh, wait. I took out the n pi. What am I doing? It's plus 1. I was like, what? Okay. Now, we have to do our little even odd case, remember? So let's say, we could keep it like this, but I like to simplify it more. So if n is even, then b sub n is going to be, let's think about this. Negative 1 squared is 1. That's 1 minus 1 is 0. B sub n is 0. If we use an odd, then we would get 2 in here, because it's 1 plus, 1 plus 1. So then that's 2 times 100, which is 200 over n pi for any n odd. So then we can go ahead and write out our solution, which gives us the heat distribution in the rod for any time t. And we can test this out with the 0-degree ends, of course. N odd, infinity. Because remember, we're doing the n odd case first. So this is 200 over n pi. E, remember, it's negative n squared. Pi squared over 1600 times t times sine n pi over 40x. Now, n odd can be written as 2m minus 1. So then we can go ahead and write this. We can pull out the 200 over pi. Could have did that before. For m equals 1 to infinity. That's 1 over n times that whole thing. So it can be e to the negative n squared. No, whoa. E to the negative 2m plus 1 minus 1 squared pi squared over 1600 times sine of 2n minus 1 m, oh come on, times pi x over 40, and then divide all of this by 2n minus 1, because it's all over n. So that would be, I think, the most simplified answer you can get. Right there. Pretty straightforward problem, but you can see it takes kind of long because there's a lot of steps. Now let's do a little check. Let's say, because remember the ends of the rod is 0 degrees. Because remember the ends are maintained at 0 degrees for all t greater than 0. So, what happened to my t? What happened to my t? Okay. So let's say x is at length. Let's test the end. So let's do x is 0. So if x is 0, let's say time is uh, 20. We should get the same answer. We should get u is 0, and then we could say that we're on the first m value of 1 from the first iteration. So let's see. We should in theory get 0 to make sure that this is correct. So u of 0, 20 for m equals 1 is 200 over pi times e to the negative 2, well, 2 minus 1 squared times pi squared over 1600 times 20 times sine of 2, sine of 0 is 0. Look at that. Because x is 0, right? So it would be sine of 0. That's just 0. It means the whole thing is just 0. So that's pretty easy. You can see that it's always going to be 0. But now, what if x is 40? Well, you're going to have 200 over pi. Let's look at that one term there. So we're going to have sine 2 minus 1 sine of pi is 0. See how that works? So we know that this equation is likely to work, and it's likely correct, because we tested the boundaries, we tested the boundary conditions, and we got the correct answer. We got the correct temperature, 0 degrees. So now I have 3 more examples of this exact same equation here. I mean, exact same scenario. Not exact scenario, but but different functions, different ranges that that's going to give us. And I'm just going to skip through steps 1 through 4, and I'm going to skip right to Fourier series, or right to the general solution, I guess. Things might change. And then I'll solve it that way, because it should be pretty easy. So I'll go through those really quick after this. And then after that, I think we're going to look at some steady state solutions of the heat equation, and then some insulated rod, or insulated ends situations. Alright, so I'll see you in the next example.